Hello. We are going to be working on the Cracking the Periodic Table POGIL today. So I'm going to give a few instructions at the beginning and then have you go and start with your groups. The first thing you'll notice if you're looking at the POGIL is that it says to obtain a card with electron configurations for your group. Those cards are in the top left-hand drawer of my desk. So here's my desk. And like you're sitting facing out towards the classroom, it should be this drawer right here. Now it's just a stack of 3x5 cards that should have, each 3x5 card has its own element symbol on it with that element's configuration. So it's not like one card with a bunch of configurations, it's a bunch of individual cards, each with one configuration on it. So I think the best way to do this is to find someone, say politely to the sub, please may I borrow the cards. I'll leave a note on the website for them. This is what they should be doing. And then divide the cards equally between the 10 teams, or 9 teams, or however many you have in your period. And everybody gets like a small stack of 11 or 12 cards or something, whatever's an even division. And then work with those cards to answer the first 4 questions before you hit the stop sign. Now I will warn you, if the cards have been shuffled, if the cards aren't in the proper order, when you get to question number 2, you may not see a pattern. Okay? You might, but you might not. So if you don't see the pattern, it's because the cards are out of order. It's okay. You'll get the pattern as we fill in the whole periodic table. Definitely once we get to the second section. I'll talk about that. All right? So also, if you don't have this printed out, if you don't have a hard copy, not everybody will, then you won't be able to write directly on the POGIL because it's online. So you can either do a PDF edit, or you can trace a blank periodic table on a piece of paper and you can write on that. That's okay. Or you can even get a real periodic table, because most real periodic tables have some room in the boxes, and what we're writing in the boxes is small. It's just the last bit of the orbital notation. So any of those options will work. So work through problems 1 through 4, and when you hit the stop sign, stop, and then you're going to pause this video now, and then you'll come back to it once you finish problem 4, and I'll take you through the next step. Okay, you should have finished answering questions 1 through 4. Your blank periodic table should have some writing on it by now. And let's see what we did. So in number 1, you've recorded your team number, and for each element you should take the last orbital notation. So I'm going to give you some examples, and I'll do my own little periodic table here. Here's my periodic table. Very accurate. So if you had something like oxygen, okay, oxygen card, the last underlined bit should have been 2p4, and you would have written that in. If you had something like cesium over here, you would expect something like a 6s1. You're just writing the last bit. Cesium had a huge line worth of stuff, but 1s2, 2s2, 3, it kept going. But we only want the last underlined bit. All right, and hopefully you filled in about 10 or so of these. So that was number 1. Number 2 says, what is similar about the last orbital notation, appearing at the end for each element in your set? Now these were originally divided into sets, but of course, like I said at the beginning, if you didn't get a set, if it were shuffled, or if you got a bunch of unrelated elements, you might not have seen the pattern. But I'll give you an example. If you did fluorine, it was 2p5, and if you did the one below it, chlorine, you would have gotten 3p5, and if you did the one below it, bromine, you would have gotten 4p5. You see where this is going? Iodine was a 5p5, etc. So the pattern seems to be, for number 2, what's similar? Well, they're all the same superscript. They all have a 5 there. 5 electrons in that level. Okay, so if you go down to 3, it says locate where your set of elements should be. Write the last orbital notation for the electron in your element in its box. So you would fill all these in like I did. And then 3b says, what's the relationship between your answer and the block? Well, look at the ones I wrote, and look at the block. This is called the P block. Alright, that thing that I just outlined there. Well, all of those things that I put in the P block had P's in them. 2p5, 3p5, 4p5, 5p5, 2p4. Anything you're going to write in there should have a P as its letter. If you had anything in the middle section here, this is the D block. And hopefully all of the elements you wrote in the D block, if you had any, had a D in them. 3d5, 5p7, whatever. Anything in this first one is the S block, and anything across the bottom here is the F block. And you should have written only those things there. So that's what you should have seen for number 3. Number 4 says, what's the relationship between the last orbital notation in the ground state and the row number on the left-hand side? Well, if you look here, the 5p5 was on row 5. The 6s1 was on row 6. Okay? The 2p4 was in row 2. Now, you would have seen that for all of the P block elements and all of the S block elements. But you probably noticed, if you had any, in the D block, you noticed something different. For instance, titanium right here is a 3D2, but it's on row 4. That might have tripped you up. You might have noticed anything in this row was a 4D element, and this row was a 5D element. Even though these are rows 4, 5, and 6, respectively. Ignore the fact that I drew cesium a little off-center there. Cesium should be in row 6. So the D block elements, their numbers for their energy levels look like they're one behind the row. If the row is row 4, the energy level seems to be row 3. Yes, that's okay. For F, you should have seen a similar pattern. Notice they put an asterisk by the first F row and a hashtag by the second F row, and then in the D block they put an asterisk here and a hashtag here. Now that's because the actual periodic table does include that. So let me draw the real periodic table just to give you an idea. The real periodic table looks like this. Yeah, no, that's right. This is the real periodic table. The S block here, the F block down here, the D block here, and the P block here, as opposed to the way I've drawn it up here, which is where I sort of chopped out the F block and put it at the bottom. The reason we use this periodic table and not this periodic table is this is too wide. Imagine how wide I would have to have a piece of paper to fit this in. Also, the F block elements are pretty boring in terms of their chemistry. They're mostly radioactive, and that's interesting. But they don't form different compounds. They largely have the same valences or similar valences. So we don't treat them that differently. We'll chop them out and put them at the bottom. Leave them be. Okay? So, but when you looked at the F block elements, what you probably saw in this row were a bunch of 4Fs, and in this row you probably saw a bunch of 5Fs, assuming you had any. But notice the hashtag, that's also this row, if these are 5Fs, but look, they're on the 7th energy level. They're 2 behind. And the 4Fs, which would be up here, they're 1 behind the Ds, and they're 2 behind the row number, the sixth level. How is that? So that's normal. You're expected to see that. P block elements should be the same as their row. S block elements should be the same as their row. If you're a 2P, you're on the row 2. If you're a D block element, you're 1 behind. If you're on the 4th row, you're a 3D. And if you're an F block element, you're 2 behind. If you're the 6th row, you're actually the 4F. Okay. So that got us through number 4. Now it says read this. It says you're going to go find the other groups. And you're going to get some elements that they had because you didn't get all the elements yet. And you're going to start filling in the rest of the spots on your periodic table. Cool. You probably won't need to talk to all of the groups. I bet as you start filling this in, the pattern will emerge. It's a very easy pattern to recognize, and you will probably be able to fill your entire periodic table in based on that pattern. You'll do that, and then you're going to go through the next stop sign. Let's find the next stop sign. Oh, the next stop sign is right after number 6. Okay? And so we'll stop there. So go do 5 and 6, fill in your periodic table, and then come back and unpause the video, and we'll go on. Okay. You should have a fully filled in periodic table by now, and I will show you what that looks like. The periodic table will be something like this. And I'm going to not actually do the whole thing, but you'll see. So S, 4, 5, 6, 7. Here we go. There are 6 P's. 2, 3, 4, 5, 6. Here there should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there should be 14 of these. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So, hydrogen, 1s1. Helium, 1s2. Okay. 2s1, 2s2, 3s1, 3s2, 4s1, 4s2. You see the pattern? Keep on going. Down to francium, it's just 7s1, 7s2. All right. It's just the left-hand one is S1 and the right-hand one is S2, and every time you go down a row, you get an extra. So here we go over here. Boron, 2p1, then 2p2, 2p3, 2p4, 2p5, 2p6. And guess what this one is? 3p1, 3p2. All right, by now you've got the pattern. Now, when you got to here, to the D block, you should have seen not 4D, even though it's on row 4, but 3D1, 3D2, 3D3, etc., all the way across to 3D10. Then you repeat again, 4D1, 4D2, okay? Keep going. When you got to the F block, you should have seen that this was 4F1. Even though this is technically row 6. I mean, remember, this fits in right here, okay, if we were unchopping up the periodic table. That's 4F1, that's 5F1, and then F2, F3, all the way to F14 at the end. 4F14 and 5F14 at the end. Okay, and that should have gotten you the whole periodic table filled in. Now, it says, count the number of columns in each of the 4 blocks of the periodic table. What's the relationship between the block size and the number of electrons that will fit in the corresponding atomic sublevel? All right? Well, we did this in class on Wednesday. In that 2-hour block, we looked at sublevels, and we said the S sublevel has 1 box, which can fit 2 electrons, 1 up, 1 down. And we said the P block, which is slightly higher than the S, can fit 3 boxes, which is 1, 2, 3, 4, 5 electrons. Now, we even talked about the D block and the F block, even though it wasn't part of the POGIL, but we did do it in a lecture. And I'll remind you that the D block is 1, 2, 3, 4, 5 boxes wide, so it can fit 10 electrons. Remember all those lobes, those weird orbitals we saw? And the F block here, that's the big one. F block can fit 7. 2, 3, 4, 5, 6, 7. So that's 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. So we've got 7 there. times 2 is 14, because 2 electrons fit in each orbital in the sublevel. So this is S, P, D, F. Well, let's compare. Check it out. The S block is 2 columns wide, and the S orbital contains 2 electrons, or the S sublevel. The P orbital contains 3 sublevels with 6 electrons total. Oh look, there are 6 columns in the P block. S, P. The D block, if you look at it, is 10 columns wide. Don't forget the D block down here had 5 pairs, or 10 electrons. And if the F had 7 pairs with 14, yep, the F block is 14 electrons wide. So we're just representing where all of those electrons are. Periodic table is your friend. All right, that's number 6. Now, the next stop sign is way down at number 16. So you've got 10 problems coming up. Okay, there's something that needs to be said though. Number 7, 8, they're going to ask you to obtain the electron energy levels handout. That is not a handout, that's actually the second video on today's web page. So this is the video that's going to take you through, the video you're watching right now, it takes you through the whole POGIL. The second video is specifically about electron energy levels and how to fit them in. Okay? And it'll help you reconcile the D block and the F block. Cool? Go ahead and watch that video, pause this one, or just come back to it later, and finish problems up to 16, and then you can ignore things like it says obtain from your teacher, a pair of scissors, cut out the sections, or don't worry about that. All right? You're just gonna go ahead and answer the questions. And I'll see you back here as soon as you're done with number 16. Okay, so you should have gone from 7 all the way up to 16. So start at the bottom of the energy levels handout with the 1s energy and locate the section of the periodic table corresponding to that level. Why are there only 2 elements in the first row? Well, there are only 2 elements in the first row because the S sublevel only has room for 2 electrons. You couldn't have more than 2 on that row. If you go up to number 8, work your way up the electron energy levels, locating as many sublevel sections as you can. Why does the second row of the periodic table not have a D block? Well, there is no 2D, is there? If you looked at that video, it was 1s, and that was it. There was a 2s and a 2p, but there is no 2D in that second section. All right. The third energy level contains a D sublevel. Why does that D block start in the 4th row? All right. The D block starts in that 4th row because you saw with the arrows we don't fill from a direct left to right, we fill on that slant. And the reason, if you mentioned the person talking in that video said, is that they're not all at the same energy level. So when we look at how much energy, and I'll try to draw it here, if we did an actual Aufbau diagram, okay, here's the S, the 1s, the 2s was here, the 2p slightly higher energy, we have the 3s and the 3p, right? Make sure we know that they're p because they have 3. And then we have the 4s. The 4s is actually here. And then the 3d is here. So let's label all this. 2p, 3s, 3p, 4s, 3d. The 3d sublevel happens to be higher in energy than the 4s sublevel. I mean, it doesn't make a ton of sense, but it's true. The 3d happens to be higher energy. So an atom will actually place electrons into his 4s sublevel before he places electrons into his 3d sublevel. Okay? So Know that. Know that. The periodic table won't help you here. It will look like the 3D stuff, like if we go up here. The periodic table just tells you that that's row 4. You have to know that even though it's row 4, only the S and P groups are the same as their row. The D block is one behind. That's a 3D. Okay? And that was shown in the video. He showed you how you do this. You do 1S, 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, 4F. And when you're filling them, you start here 1S, then 2S, then 2P, then 3S, then 3P, then 4S, and then 3D and 4P. And consequently 5S after that, if you keep going. Alright, so if you remember how to do this diagram, you just start at the top. There's a 1S, then there's 2, then there's 3, then there's 4, like this all the way down. You should be able to recreate this diagram when you need it. So that answers 8B. Why does the D block start in the 4th row of the periodic table? It starts in the 4th row because it's directly after this one, which is the 4S. It's higher energy. Number 9, key idea. For the elements of the D block, how is the row number related to the principal energy level for the last orbital notation of the electron configurations? The row number for the D block is 1 behind. So if you're in row 4, you're a 3D. If you're in row 6, you're a 5D. You're behind everybody. Think about it. Students who are getting Ds, they're a little behind. Obtain from your teacher the periodic table handout and a pair of scissors. We weren't going to do that. There's nothing to cut out. Go to 11. Use your groups, reconstruct a periodic table to label the sections of Model 2, starting on the left, and that's the one I drew here. Where did I draw it? Oh, come on, Kip. There it is. Those are your sections, S, F, D, P. Compare the periodic table of Model 1 with Model 2. What section was removed? F section. What did the asterisk and hashtag symbols mean? Okay, the asterisk and hashtags are to tell you where you're supposed to be going. If you start at the 6th row, you keep going along from here down to here, and when you get out of this way, you finish back up into this row. The form of the periodic table seen in Model 2 is the long form. You do not often see this. What are the disadvantages? Too wide. Way too wide. Why does the F block not appear until the 6th row, and why does it fit in between the S and D blocks? Okay, well, it has the same. It's the same thing to do as this over here. The F block doesn't come in until you're way over here. F is 2 behind, and so if you think about D's, D students are a little behind. F students are 1 more behind. They're behind the D students. Okay. So if you look at number 16, what is the relationship between the principal energy level and the row? So we said over here, we said if you're on row 4, you're a 3D. You would actually be even less than that if you're F, but there is no 2F. But if you're on row 6, you're a 5D, you're a 4F. Because you're behind the D block by 1, and you're behind the row number by 2. Okay, number 17, key idea. Write the last orbital notation in the electron configurations for the elements located at A, B, C, and D. You should not have to count electrons to do this if you understand the structure. So I am going to attempt, well, you can see it. You can see it. So I'll just draw a real quick periodic table. Here's your periodic table. Mr. Kip can draw. Here we go. And I see an element here, and an element over here, and an element here, and an element here. I'm not going to draw the whole thing, but you can count them because you're looking at it. It's right in front of you. So A is the 4th column down Fourth row down, first column over, and it's in the S block. It is a 4s1. B is in the sixth row, except that it's a D block, so I have to take one away. So it's actually a 5D. And if I count over 1, 2, 3, 4, 5, it's a 5D5. Okay, C. If we look at C, fifth column down, that's a 5. And since it's a P block, it's the same as its row. And it's the fourth one over, so it's a 5P4. And lastly, D, if we go, that's in the F block. There's only a 4F and a 5F, so this is a 4F. And I count over is the 11th in its row. It's a 4F11. Okay, so that should be your number 17. Okay, so now that's your stop sign. I just did 17 even though it's past the stop sign. Well, you get that one for free. So you're going to go from 18 down to 22. You guys are going to finish off the POGIL and then refer back to the video. So go ahead and finish, pause the video, and then come back to it. Okay, so 18. Now that you understand how the structure of the periodic table relates to electron sublevels, you can use it as a cheat sheet. This is great. We really were looking forward to this. So it says, go to vanadium, V. Use your finger to trace a line across the top of the row. Explain why the two boxes in that row represent 1s2. So if you look up above 18, see the first energy level? It says 1s2 on the right. And I'll draw that here. Let's do a clean periodic table here, more or less. All right, periodic table. It's like this. And there's a dotted line on your thing going over like this, from hydrogen to helium. And it says that's a 1s2. This is like kind of the one exception on the periodic table. We always write helium in this box, but the way it's written, it looks like it should be in the P block. The problem is there is no P orbital at the first energy level. There's only an S orbital. So helium is a 1s2 electron. He's the only one over there that looks like he should be P but isn't. Everybody else in the periodic table fits where they're supposed to. So when it says trace your finger over, explain why the two boxes are 1s2s, alright, it's because there is no P level. Alright, part B, trace a line across row 2, explain why this is 2s2, 2p6, right there, that's a 2s2, 2p6, because you hit, as you cross that line, you hit this one, that's a 1s1, 1s2, 2s1, 2s2, 2s3, or p4 rather, p5, and p6. Okay, as you fill in those boxes. So that element has electrons filling up the alpha until it gets to 2p6. C, trace it across the row 3, record the sublevels of electrons that will be filled. So row 3 is a 3s2 and a 3p6. And then cross row 4 until you get to vanadium. So we're stopping here at vanadium. Well, we went through these, so vanadium will also have a 4s2, and then we went through 1, 2, and he's the third box in the D row. Remember, that's a 3D. So he's a 3D3 electron. Okay? And then it says combine the steps to write a full ground state electron configuration. There it is. I'll write it out down here. Vanadium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. That's vanadium. If we're filling Aufbau diagrams, we definitely fill all of these first in that order, but the last electrons wind up in the 3d3. Cool. Going on to 19. Using only a periodic table, write the full ground state electron configuration for tin. Well, tin is down here somewhere. Sn. And because my periodic table doesn't have Sn, I'm going to look that up just to make sure I know which one I'm looking at. Yes, okay. Sn is on row 5, and he's in this column, column 4. Not column 4, column 2. Or the second P column. So, Sn, the full electron configuration, I have to get to 5p2, where he ends up. That's nuts, but we'll do it. 1s2, 2s2, that's this first one here. Go down row, 2p6, 3s2, 3p6. Once I get to the fourth row, 4s2, I start getting d electrons. I get the 3d10 this time electrons, and then I go to the 4p6. Okay, that gets me all the way across row 4 to the end, and then I start again on row 5. So now I'm down to row 5. I should hit 5s2. Okay, and then I get to the 4d10, and then, sorry, I gotta keep going, I'm out of room here. I get to the 5p, but he's in the 5p. He's 2 over. He's a 5p2. Quite a bit. So looking, can I fit that all on one screen? Not quite. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. Okay, that's a mouthful. So that will be tin's ground state electron configuration. A lot. I'm going to tell you right now, we usually refer to tin as a 5p2, and that's what we need, because you imply that all of these are there, and only the outer electrons do any interesting chemistry anyway. So, but this is the full, if it ever asks you for full ground state electron configuration, make sure you go through everything before it. Now, I'm going to do this with 20. Electron configuration for some unknown element. Look at how big that is. That's huge. A, identify the element, write its symbol. All I care about, though, is this, the last bit. So I'm not going to write the whole thing out. I'm just going to write the last bit. 6d4. That's all I need. Now, it's a D, and D's are one behind. So I'm not going to look in row 6. I'm going to look in row 7. I'm going to look in the D block. 1, 2, 3, 4. So I'm going down here to row 7, and wherever that intersects should be my element. And when I look there, the 4th D and the 7th, I see this element, Sg, or seaborgium. Okay? Seaborgium. B, describe 2 different methods that can be used to identify this element. The one I did was just going through based on the final configuration. You could also do and count across the 1s2, 2s2, 2p6, 3s2, 3p6, and just keep going and use the whole full configuration until you got to the 6d4. You are welcome to do that. But it's time consuming, and I really don't recommend it. On to the last questions. This is 21. For each of the elements in Model 4, circle the portion of the true electron configuration that differs from the predicted electron configuration. Alright, so this is where we start to get into the tricky stuff. Chromium. Chromium has a predicted configuration of 3d4, specifically 4s2 3d4, but it has an actual configuration of 4s1 3d5. That's going to mess you up, right? So we're circling that. It says circle, I'm just writing it down. So copper, actual, the one that matters, is 4s2 3d9, but, or sorry, that's the predicted. That's what we say on paper. If you were just looking at a periodic table, you would think copper's a 3d9, but it behaves like a 4s1 3d10. Okay. And cerium is, yes, it is a, I'm trying to get this straight in my head, yeah. A 5p6, actually the p doesn't change, does it? It's a 4f2. That's what changes, isn't it? I had to look at it for a second. And what it changes into is a 4f1 5d1. You like my penmanship there? It's a 4. 4f1 5d1. All of these are exhibiting a similar behavior. And it says in 22, construct a possible explanation. Well, here's the explanation. If you were to draw an Aufbau diagram for chromium, this one, it would look like this. You would get to the 4s level, and you would expect this one. And then remember the 3d is just slightly above the 4s, like this. And the 4p is just slightly above. They're all very close in energy. Or sorry, yeah, the 3d, so 4s, 3d, 4p. These are your sublevels, 1, 2 here, and 1, 2, 3, 4, 5 here. That doesn't look even, but it is. Make sure it has 5. So when we look at chromium, it was originally 4s2 and 4 in the d orbital. That's how many it fit. That's what we think chromium should be. And yet, what's really happening here is that chromium takes this s electron. I'm going to delete an s electron here. No, I'm not. It won't let me. So I'll just redraw it. That's technology for you. So this is expected. Here's actual. You have a 4s with 1 in it, and a 3d with 5 in it. Look at that. What happens? Well, look how close in energy level these two are. They're very close. And there's another thing going on. When you have these guys all lined up and all spinning the same direction, and there's 5 of them and they're at the same energy level, there's a harmony there. There's a resonance that keeps them at a nice stable state. They like that. They like all being lined up and half filled. There's a certain stability associated with that will actually lower their energy level. It makes it more energetically favorable. And then you also have this guy. He's also spinning the same direction in his s orbital, which is almost at the same height. So you have like 6 electrons all humming along together at the same spin. This is actually more stable than this up here, where you've got them split and the one off the one pair. So what chromium does is it takes this electron and promotes it to the d orbital in order to lower its energy, which may sound off, but there's that stability it reaches with that 4s1 3d5 configuration, and we see that. This behavior, by the way, is part of the reason that the metals in the when we were doing, remember we did ions first semester, and we said transition metals, some of them are +2, some of them are +3, some of them are +5 or whatever. This is the reason. Because when we look at orbital notation, they have the ability to promote an s electron. And then there's only one s electron that's available to be taken away, and then you only get a +1 ion, instead of having 2 valence electrons like we expect. That's where that comes from. Interesting stuff. Okay. And you can imagine similar things happen in the other two. So in copper was a 4s2 3d 9. What it does is it promotes that s electron to the d's, so the d's are completely filled. Completely filled is very stable. And then you have an s that's half filled, and half filled is sort of stable. Okay, there's a certain symmetry there. This configuration is stable enough that it prefers it, and it will promote an electron. So copper, if you had it like this, these d electrons completely filled don't want to go anywhere, so it would only lose the one s electron and be a +1 copper. But if you have copper in this state, which is possible, sometimes they fluctuate, then you have 2s electrons to lose, and you can get a copper +2. Copper has a +1 state or a +2 state. So this orbital notation explains things that we could not have explained if we were back using the Bohr model. Okay. Hopefully this answered or brought to light a lot of things that you were misunderstanding about orbital notation. You should all be pros. You should be able to use the periodic table to predict orbital notations. And we will continue with this on Monday. Good luck.